This is a chapter review for chapter 3, derivatives. The derivative of a function is the function f prime of which the value at x is this limit as h approaches 0 of the quotient. Of course, the limit should exist. That limit is the same as the slope of the tangent line here that y call fx, then point here that is now x coordinates x, and vertically the value will be f of x. At the point, the slope of the tangent line, and that here, this slope is now f prime, okay, at x. Okay, we have a remark. The domain of f prime may be either the same as or smaller than the domain of f. And f is differentiable at point C, then at the point f must be continuous. However, the reverse is not true in general. Okay, let's try to solve examples. Let f of x is 1 over x. Use the definition of derivative to find f prime. Okay, let's try to use definition to get the derivative of fx. Okay, here, part A. And f prime of x must be same as limit. We are using the definition h approaches 0, f of x plus h minus f of x divided by h. Okay, we'll rewrite this portion. That is same as, now f x plus h is same as 1 over x plus h minus 1 over x divided by h. So we'll try to manipulate the top. That is now x plus h, and x is common bottom, and there is x minus x plus h, and here divided by h. Okay, this portion is minus h, and along with this h, it can be cancelled out, so that there is minus 1 over x and x plus h. Right? Okay, so once h approaches 0, then that will become minus 1 over x squared. So that's the final answer. Now we want to find the tangent line to the curve y call f of x at x equal 1. So here we have to find the point and slope. X is 1, means that f of x, which is 1 of x, so it is 1. So from here, we know that the point is 1 and 1. Now, how about the slope? Slope is now can be found by using the derivative f prime at 1. So that is same as minus 1 over 1 squared, which is minus 1. So from this information, we can get point slope formula for the tangent line. Okay, that is minus y minus 1 equal minus, that's the slope, and x minus 0, which is 1. So we can get this equation. You can simplify if you want, but you can leave it in this way. Okay. Now, chain rule. At this moment, I believe you understand chain rule. The main idea is you try to get a group of expression and consider it as U or g of x, and first try to make derivative with respect the group, and later on you can multiply the x derivative of the group. Okay, that's the main idea. Okay, let's go to this example. Find the value of f composition G prime at given value of x. And, okay, and here find an equation of tangent line to the curve at the given point. Okay, that is the given point x equal 1. Okay, now first we have to find the derivative. Okay, now f of u is u to the 5 plus 1, and u is function of x and square root of x, so that if you try to write down f as a function of x, then that will be now square root of 5. No. Sorry about that. Okay. Square root of x to the 5 plus 1. That is f as a function of x. But you can write in this way, so that by using chain rule, okay, that is some extra one. But anyway, by using chain rule, you have to differentiate with respect to now u, so that df over du and times du over dx. That is chain rule. Okay, so it's a 5 times u to the 4, and here that is this portion, and u x derivative will be same as half and 1 over square root over x. So that, okay, from this one, the constants are, can be written as 5 over 2 and u to the 4 and 1 over and square root over x. Now, u is square root over x, so that if you plug square root over x here, then that will be x squared and minus half power, so that there is a 5 over 2 times x to the 3 over 2. So that is derivative. Okay. Now that is first part. Okay, that is the first part. And second part, we have to find the tangent line. Okay, we're at x equal 1 here, so that the slope is now, and when x equal 1, then there is definitely is a 5 over 2. Here, if you plug here 1, then only this coefficient will appear. And the point is, now, x equal 1, then here f of x or f of u is same as 1 to the 5 is 1 and plus 1, so that is 2. So the point is here 1 and 2. At the point, the tangent line can be written in this way. Y minus y0 equal the slope and x minus x0. Okay, so that is the point slope formula for the tangent line. Okay, now derivatives of inverse functions and logarithms. By using chain rule, we can derive this equation. Here, main idea is that f inverse, derivative is same as 1 over f prime. Now, when you try to evaluate this term, then you have to find the corresponding point, because here originally, now okay, there's domain and there is a range of f, and f inverse is now, that will be domain of f inverse, and this side will be range of f inverse. So here x, okay, in this notation, x is now in this area, the right side, but f is defined only here, so that you have to find first the corresponding point here, and then you have to evaluate f prime at the point. And so along with that identity, you can get it. As you can see here now, and f of x, y equal f of x is given in this way, and y equal f inverse of x is given in this way. At this point, the slope, and we want to find the slope at the point, but that is reciprocal of the slope of f here. But here the evaluation point is completely different. Now that is around here, that is around 1, right? So you have to find the corresponding point. So let's go to this example. We want to find here f inverse derivative evaluated at 7. And so you have to find, okay, right now, this is domain and range, and f is defined in this way, and f inverse is defined that way. We want to find the slope of f inverse at 7. So you have to find the corresponding point. If it is x, then fx must be 7. By solving this equation, you can find the corresponding point here. So f of x is x squared minus 2x minus 1. That is 7. That means that here x squared minus 2x minus 8 equals 0. And 2 for separation with minus and plus. That means that here now x is minus 2 and 4. But here, to have inverse, it must be 1 to 1, so that the domain is restricted along with that inequality. X must be smaller than 1. So here, from here, can get x equal minus 2 only, right? So the given quantity, that one is the same as, okay, the quantity is same as 1 over f prime at minus 2, right? So let's try to get f prime at minus 2. First, f prime is same as 2x minus 2. From this, we can get that. So here, now f prime and minus 2, that is same as minus 4 minus 2, so that is a minus 6, right? So the answer is minus 1 over 6 is reciprocal as the solution. Minus 1 over 6. Okay, that's the final answer. Okay, now derivatives of logarithmic functions. And once the function is logarithm with general base a and x, then now that is the same as, in fact, we can solve for x, and then it will become here exponential function. Now e and natural logarithm are inverse each other, so we can write in this way. And now by using power rule, y can go out in front of logarithm in this way. We can use this identity for some cases. Now here, if we make implicit differentiation for this equation, then that is 1. And then now here, by using chain rule here, and e to the y log a, and derivative of that term is given in this way. So now we can solve for y prime, and here also we replace y using here x terms, so that we can reach at that one. In fact, e to the y logarithm a, that one is same as x, so that we replace this part with x. So y prime is 1 over x natural logarithm a. Once y is given in this way, then you can get that. Here we have a formula. So for logarithm ax, the derivative is given in this way. Now, once a is e, then there's a natural logarithm. So that natural logarithm e is 1, so we reach at that one. Now, here, similarly, we can get the derivative by using some logarithmic technique, such formula, and now a is e, then that is 1, so we reach at this one. And by using chain rule, in logarithm of fx in derivative, that is f prime over f. And now here, even though here x can be negative, and along with the absolute value, it becomes positive. And this is a special case of that one, so that logarithm absolute value of x is derivative as the same as 1 over x. Okay. Okay, here we have some technique to get derivative, and very useful technique in logarithmic differentiation. And for the expression, and you can take natural logarithm and differentiate implicitly and solve for y prime and replace y with f over x. Then you can get derivative. Let's try to get here derivative by using logarithmic differentiation. Okay, yeah, y equal x natural logarithm x. We are taking natural logarithm both sides. Then natural logarithm of y equals same as natural logarithm of x and natural logarithm of x. That's the power, so that by using power rule, it can go out. Then now is natural logarithm of x squared. Now we can differentiate implicitly. Then from this one, it'll become y prime over y. Now that is same as 2 logarithm x times 1 over x. By using chain rule, you can get it quite easily. Okay, so here we solve for y prime. So y prime equal now 2 times here, okay, y will be here, and then there is a natural logarithm x over x. What is y? Y is this one, so that it will become 2 times here x to the natural logarithm of x times here natural logarithm of x over x. That's the final answer. Okay, for this one, y to the x and x to the y. And once in expression you have a power, then mostly the technique to get the derivative is the logarithmic differentiation. So we apply logarithm both sides. So that is a natural logarithm y to the x equals same as natural logarithm x to the y. From this one, by using power rule, we have x natural logarithm of y equal here y times natural logarithm of x. Now we differentiate implicitly. Then now here again, product rule must be used. Okay, natural logarithm of y plus x times the derivative of that term is same as y prime over y. Okay, right side, that is y prime and natural logarithm of x plus now y times 1 over x. Okay, we move y prime and left hand side, the other terms go right side because we have to solve for y prime. From here, we have a y prime. Now, originally we have x over y, and that is moved from right side. So it's a minus natural logarithm of x. Okay, here, and originally we have y over x on the right side, and that one, natural logarithm of y will be moved to right side. Okay. So now from this one, here y prime, okay, now y prime equal, okay, y over x minus natural logarithm of y divided by, and here x over y and minus natural logarithm of x. Okay. Now for this term, originally the function is given defined implicitly so that there's no way to replace y with f of x. So you can leave it in this way. So this is final answer. Okay. Okay. Now that is one exercise problem you already solved. We'll do it again. Yeah, suppose that the function f and its derivative have the following values at 0, 1, 2, 3, 4, and there's x and there's fx value. Assuming the derivative of f inverse is inverse of the f inverse, the inverse function f inverse is differentiable, find f inverse prime at such point. Let's try to do only that one. Then we have to find basically f inverse prime at 2. So again, you have to consider in your mind this picture. F is defined in this direction. F inverse is defined here in this way. You have to find the slope of f inverse at 2. So here, now if you are using the formula f, okay, inverse prime equal 1 over f prime, then you have to find the corresponding point here. So that point, okay, that is 2. In over there, that's exactly this 2. Then now the corresponding point here must be 3. So that you have to find here 1 over f prime at 3. What is that? That is now 2 over 3. So 1 over 2 over 3, which is same as 3 over 2. Okay, that's the final answer. Linearization and differentials. If f is differentiable at point A, then the approximating function Lx is given, okay, that is basically the tangent line, and is the linearization. In definition, we say that is a linearization. And once the function value is approximated by using L of x, then that is called a linear approximation or tangent line approximation, because the equation is basically a tangent line at a, f of a. Okay, yeah. And also differential is defined in this way. And dx is independent variable, and dependent as a dependent variable, differential dy is defined in this way. Yeah, dy is f prime at x and dx. Yeah, once you define this way, the question is, what is dy? Dy, and because we often choose dx as now delta x, a change in x, so the dy will be change in the linearization, change it through the tangent line. So basically, that will be delta L. We'll see here from this example. F of x is 2x to the 4 plus x, and now find the linearization at 1. Okay, part A. And the point, if x is 1, then now f1, that is the same as 2 times 1 plus 1, so that 3. The point is here 1 and 3. Okay, and now we have to find the slope. So f prime at 1, in fact, f prime is now 8x to the 3. Okay, for that one, and plus 1. So here f prime at 1 is the same as 8 plus 1, which is 9. So here L of x, that is f of 1 is a 3, so 3 plus f prime at 1, that is 9, and here now x at x0, which is a. In fact, we are using notation a, x minus 1. So we can rewrite this one in this way. There's a 9x minus 9 plus 6 plus 3, so that 9 is 6. Okay, that is the linearization. And use Lx to approximate f 1.1. So here, part B, f 1.1, rather than along with 1.1 we evaluate, rather than that we try to use L 1.1. So there is approximation that is now 1.1. Okay, so let's try to use this portion. Then here 3 plus 9 times 1.1 minus 1 is same as 0.1. So it's 0.9, so it's 3.9. That's the answer for part B. Practically, if you try to get the exact value, that is about exactly that value here, and about the difference is about 0.1. Okay. Now part C, we want to find the dy when x is 1 and dx is 0.1. Okay. By using that formula, okay, here dy equals same as f prime at 1 and dx. dx is now 0.1. Okay. And f prime at 1 is, we already know, is 9. 9 times, okay, 9 times 0.1, which is same as 0.9. Okay. Here, And that 0.9 is the same as that one. Okay. And pictorially, right now, f(x) is given in this way. The tangent line, oops, okay. Let's try to make it a little bit better. Tangent line is given in this way. Okay, that is now here, x is 1, and the value over there is basically 3 right now. Okay. Now, dx is 0.1. So after 0.1, now along with the tangent line, the value is changed here. So that tangent line, the value is changed. That portion is 0.9. So from 3 and now change in tangent line is 0.9. Okay? That is the same as this one. Okay. Okay, this is the end of chapter 3. Thank you.